but the understanding of how Mother Nature formed the hills is not so apparent. The geological story has many parts, each filled with fascination. Here on the outer rim of the Black Hills is one of the stories found in petrified wood. These stone trees of today were the living plants of 120 million years ago. But explaining the presence of petrified wood is like trying to understand a book by reading only one page. So let's try to organize the sequence of events that created the mystery and beauty around us. Let's begin our story by telling you that the Earth is about 4,600,000,000 years old. The molten matter that made up the Earth first solidified by cooling into crystalline rock. The Earth did not form instantaneously, but rather over a very long period of time. Even after the first rocks were formed, the Earth was still tremendously hot and uninhabitable, with all kinds of volcanic activity going on. In other words, it was the formative time of the Earth. Geology is the study of the Earth with all the physical features of land and water being a part of it. Tremendous strides have been made in the amount of knowledge of the Earth in the 150 years that geology has been a science. As in any other discipline, attempts have been made to make order out of chaos, and part of this order has to do with the 4,600,000,000 years of the Earth's existence. An arrangement of 4 eras cover all of this time. The earliest is called the Precambrian, the aforementioned formative era of the Earth. The next is called the Paleozoic, which means old life, the Mesozoic meaning middle life, and Cenozoic representing new life. These eras are further divided into much shorter time spans called periods, and some of these yet into epochs. Usually a major geological event has occurred to divide one from the other. Now we're going to limit our discussion to what formed the Black Hills and the rock layers exposed by the uplift and the subsequent erosion. We have rock layers from practically every one of the periods, and the Black Hills are one of the strangest geological rock structures on Earth. Our explanation will be in simple, non-geological terms so that all may understand. The Precambrian was some 3.8 billion years in length. That's 5/6 of the total time of the Earth's existence. Bits of matter in space collected to form the ball of material in orbit around the sun, and as the millions of years passed, the outer layers began to cool and crystallize and form the Earth's crust. Even as it exists today, the crust is only 25 to 45 miles thick, and the center still being in a molten state with the surrounding layers ever so slightly cooler towards the surface. It was during this Precambrian era that an upthrust of molten rock formed the roots of the future Black Hills, but by no means the hills as we know them today. One must remember that rock layers are laid down by various means over long periods of time, with the oldest on the bottom. These basement rocks are mostly the igneous type, at one time molten but now hard and crystalline. The second type of rock is called metamorphic, meaning changed from their original state by pressure and the resulting heat, but not molten. The third type of rock generally found on or near the surface is called sedimentary. We will show you examples of all of these as we inspect the Black Hills rock layers. There are 6 basic types of rocks that make up the original undisturbed layers that were present before the Black Hills uplift. The oldest were the so-called basement rocks of the Precambrian era, mostly of granite and other igneous types. As the crystalline rocks eroded away into smaller bits and pieces, they reformed into another type of metamorphic rock called schist. Now, we'd be remiss if we did not mention the action of wind and water at this time that were greatly responsible for breaking down the surface rocks and transporting the smaller bits to ever change the landscape. Water and wind serve as land levers and are the 2 greatest factors in the erosion process. Water also covered a good part of the western continent during the late Cambrian era, but we had not recognized North America as it was still attached to Europe and Africa in a huge supercontinent called Pangaea. We'll have more about this later. As we advance in time, through the Ordovician, the Silurian, and the Devonian periods, we find practically no deposits left in our area. But as the Mississippian, the Pennsylvanian, and the Permian periods roll by, we find that 4 major seas have advanced and receded, leaving us some 1,700 feet of limestone on top of the Precambrian deposits. Now, limestone is made up of the tiny dead bodies of plankton and other sea life that settles to the bottom. It's mostly calcium. It makes up the thickest single type of rock of the 6, except for the basement rocks. Now, the seas receded. The climate changed from the rainy, wet, swamp-like environment to a dry, arid climate with very little rainfall. Iron-rich sediments, probably of volcanic origin, were exposed, causing the western red beds. Some 700 feet of these red sediments make up the next layer, locally called the Spearfish Shale. It occupies a very prominent place in the visible Black Hills geology. On top of the Spearfish redbed layer is some 5,000 feet of sandstones from the Jurassic and the Cretaceous periods. It is also during this time period that extensive mountain building had begun in the western part of this continent, and this in turn was caused by what we call plate tectonics or continental drift. The continent by this time had broken away from the Eurasian landmass and had drifted to the north and west. The Black Hills area would have been in latitude about where South Texas is today. Of all the rock layers and types that we have mentioned, only one contains any petrified wood. That particular sandstone of this early Cretaceous period is called the Lakota. It's up to 400 feet thick in places, and it represents a few million years of tropical, swampy environments. The 6th and last major type of rock was deposited by the Pierce Seaway connecting the Arctic Ocean and the Gulf of Mexico from north to south. Minnesota to the east gate of Yellowstone Park, east to west. Marine sediments anywhere from 1,200 to 2,000 feet thick covered the area when the water finally receded about 65 million years ago. Collectively, there were some 12,000 feet of sediments on top of the Precambrian rocks that were deposited over a period of about 535 million years. Now imagine these 6 layers as a stack of blankets, each with its own color and thickness. Further imagine a fist under the stack, pushing up in a central location, slowly elevating the layers into a dome. You can readily see that the order of the blankets has not changed, only their shape. The top of this stack of blankets would be about 12,000 feet above today's sea level. This would be the approximate altitude of the Black Hills Dome as the uplift ended some 34 million years ago. Now let us digress for a minute to compare the structure of the Black Hills versus other mountain ranges. Mountains are usually upthrust because of lateral pressures, not vertical pressures. If lateral pressures would have been exerted on these layers, we'd have this type of mountains found throughout the world. The lateral pressures on the continent takes the layers we have described, breaks them into pieces, lifts and shoves one over the other by overthrusting and faulting. This overthrust causes our mountain ranges, and they usually form in a line at about 90 degrees to the direction in which the forces were applied. Now we can begin to understand the Western Basin and Range Complex just a little. But the Black Hills are different. The fist, or vertical pressure, made the dome oval-shaped. Domes are well known in geology, but usually less than 5 miles in diameter. This one is about 135 miles on the north-south axis and about 80 miles on the east-west axis. The dome eroded away almost as fast as it was uplifted, because most of the blankets were of sedimentary origins. This erosion has removed hundreds of cubic miles of sediment from the dome. If you can imagine our blanket stack with the top cut off by a big knife, it is easy to see the odd rifle target-like pattern of the rock layers. The eroded cut-off top was transported downwind and downstream and redeposited in the area adjacent to the dome on the east side. Subsequent erosion of these deposits have caused a huge waste area called the Badlands. With some basic understanding of the Black Hill structure, we may now go and look at the actual layers. A short car trip starting at Mount Rushmore and ending near Rapid City will take us through 5 of these rock types and give us a view of the 6th. Harney Peak, which is just in back of the President's, was the center of the fist. It now stands at 7,242 feet above sea level. Compare this to the 12,000 feet that it used to be. This is the original Precambrian upthrust made of granite, which of course is igneous rock. Just to the south of Harney Peak, and still a basic part of it, is the Needles area. Vertical spires of granite indicate the direction from which the dome building pressures came from, as they are the remnants of pressure cores. Just remember that this granite area was covered by thousands of feet of sediment. Try to visualize the tremendous pressures it would take to lift this mass upward several thousands of feet. But such as it was, in the Eocene epoch some 35 million years ago. But as our knife has cut off the dome top and exposed the layers, we'll proceed away from the uplift center, Harney Peak, and go down the mountain following Highway 16A towards Keystone. A short distance from Mount Rushmore, we see the first contact of 2 different kinds of layers, the granite and the schist. Proceeding on through Keystone, still surrounded by schist, and towards the village of Rockerville, we again notice a definite change or contact of 2 different kinds of rock. This is the start of the Mississippian limestone that was laid down about 345 million years ago. We're going up the time scale from the oldest rocks in the middle of the hills to the newest on the outer rim, layer by layer. Now, as we continue towards Rapid City, limestone is the basic type for several miles. As we approach the bottom of this hill where the reptile gardens are located, we change from limestone to the Triassic red beds. On across the floor of the Red Valley, which, by the way, is a valley all the way around the dome, we change to the sandstones of the Jurassic and Cretaceous periods. Climbing this steep hill, we are going up the inner face of the hogback, the continuous rim of sandstone that is a ring around the dome of the Black Hills. Looking east over the prairie, we are actually looking first at the wind and water sediments from the dome, but just underneath is the Pierre Shale, the marine deposits of the late Cretaceous. On a clear day, the Badlands are clearly visible from this vantage point, even if they're about 50 miles away. In a distance of about 22 miles, we have looked at rocks from the Earth's beginning to sediments that are forming rocks today. Is it any wonder that geologists from all over the world come here to study in much more detail the rocks that you've just seen on this short trip? Proceeding northward through Rapid City, up the Red Valley, we arrive at the Black Hills Petrified Forest. We've looked at the big picture of the hills. Now let's examine one page of our geological book in more detail. About 120 million years ago, that is early Cretaceous, no Black Hills, no western mountain ranges, we find ourselves in the middle of this huge tropical swamp. Cypress trees are everywhere, cycads, a plant that looks much like a short palm or a huge pineapple grew all around. There were reptiles, some fish, a few insects, all quite at home here. It has been said that the modern Okefenokee swamps of Georgia are almost exactly like the early Cretaceous swamps of this area, except for the very large reptiles that do not exist today. The cypress trees of then are the petrified logs we see lying about now. If we start at the beginning, perhaps we can understand a bit more about nature's handiwork. The word Petra comes from the ancient Greek and Latin word for stone. To petrify literally means to change to stone. It's a process where each tiny portion of the wood has been replaced in its exact form by minerals. It's a process requiring much time, although no one can say how long, because no laboratory process can equal nature. The trees died, as all living things do, eventually fell into the waters of the swamps and sank to the bottom. The water was probably very stagnant, that is, low on oxygen, and that would reduce the oxidation or rot to a minimum. In time, sand was carried into the swamp, possibly by seasonal rains that gradually covered the logs. As the millions of years rolled by, it left this one layer of sandstone, some 250 to 400 feet thick, that contains the petrified wood. Wood is relatively porous. That is, microscopic inspection of the wood shows more area of open passageways than solid wood. This allows the water to penetrate and saturate the total log. The water is highly charged with molecules of silica, the basic material of the surrounding sand, and for some reason it displaces the molecules of wood. It is suspected that the swamp water was slightly acidic, enough to chemically break down the wood to be replaced by the heavier silica molecule. Eventually, there's no more wood, no more passageways, as everything has been petrified, or, that is, changed to stone. One of the most popular misconceptions of petrifaction is that it's caused by pressure. Examination of cross-sections of petrified wood show that there is no distortion of the original cellular structure which pressure would surely have caused. This inspection under the microscope also gives us a means of identification. Each species of tree has a different cellular arrangement, therefore petrified wood samples may be cataloged just as though they were live trees. Many species of trees that grew in this area during early Cretaceous time have been identified, but cypress being the predominant. Why is the petrified wood now exposed on this hill? Was the swamp water deep enough to cover this hill? No. The Black Hills were not to be uplifted for another 80 million years, and if that had never happened, this wood would still be buried under hundreds of feet of rock layers. The Black Hills uplift of the Eocene period and the subsequent erosions has exposed the wood in the Lakota sandstone. We hope that this information has been helpful to you and has broadened your geological knowledge of the Black Hills, one of the most unique areas on the Earth.